Welcome you all for the Lab 2 session. As we did earlier, we'll see few more problems, and I wanted to add more today, but somehow I felt this itself will take 2 hours, so I'm not planning to add. But let us see, if we need, we can always add more to this based on the speed. I'm not going to rush it up. So let us do the same thing like what we did. I will show you the problem. I will open up the chat. You can start discussing. Okay, so this is the problem. By now I think all of you are paying attention to this code. This is getting called, and what will be printed. Okay, so we will open it up for discussion. Question 6. Let me keep it close to this. So no problem. Okay, anybody else? Okay, okay. So what is happening here? We are declaring a variable, local variable, local variable pointer, type pointer, and it is getting the address of the I. And then my function, which is defined to be int star, that means it is accepting pointers, and we are passing a pointer of this integer. So what is being passed is an address. Now first thing what it does is, the function on entering, it is printing it. So it will start with, as you all said, it will start with 10, no doubt about it. And then it is checking whether ampersand of, exclamation of star of IP. Now what is happening here is, it is accessing the value. To start with, it will be getting the value 10, and then it is checking whether it is a non-zero value or not. So ampersand of any non-zero value will result in false. Sorry, not ampersand, I'm just exclamation mark, not of 0. So if it is a 0 value, it will be true. So if it is not 0, that means it is not going to return, because it is going to return a non-zero value. Here will return a false there. So it is going to come down, and then it is decrementing the value which is being passed. So star of IP minus 1 star IP. So it is updating the decremented value into the same place. That means this variable is getting changed. If you print it here, you will see that the value is changing. Now after that, it is going to recursively call the function. So it is passing the same address and then going across. So as you guys guessed it, it is going to be keep on going down, but there is a doubt in the minds of some people. One person corrected it afterwards, whether it will print 0 or not. So the fact that the checking of 0 is happening after printing, so it will print 0, and then when it becomes 0, it will become true and it will return from the function. So there is no recursive call. So everybody will wind up out. So nothing will, what you will see is these values getting printed from 10 to 0. Okay, it will be from 10 to 0. Most of you got it right. I don't know who, those who are not answered might have got it properly, I hope. Is there any doubts on this? Even if you got it right, or if you got it wrong, or you are still not able to get it, you can tell me. I hope this is clear. So let us run it on the IDE to be sure. Oh, what happened? Okay. So I don't know whether any of you, whether you are using this particular IDE or some other IDE. I am not worried if you are having something else. So 10 to 0 is correct. See, one thing, if you are running on Windows 10, because this code block is from not from a registered vendor, it says this is invalid and doesn't allow Windows 10, or if you are having any McAfee or some other antivirus, it may not allow the executable to be running. Okay, exe it will disable. So you may have to either disable the firewall, or you have to selectively say that exe can be run. Where Windows 10 has a very strict, and McAfee also is having a very strict regulation that the exe files generated by unlicensed software, or which vendor is not registered, it might give error. So you might feel there is some problem in running the executable on Windows 10. Windows 7, no problem. In case if you have any problem such like that, please handle it. Either you disable any McAfee or something, or start the Windows code block in a administrative, right click and then run as an administrator. Maybe it will solve some problems. Okay, in case if you get into any trouble like that. Okay, fine. Okay, any other? Okay, no questions, so we will go ahead. Even if you are having anything related to this, you can ask me. Okay, now another question. Okay, we will start. It's not very difficult. So what is getting done here, what is being done is we are calling the function 2 with a pointer, which is a pointer to the variable I, and similar like that whatever I showed you, here, and then it is accessing the value twice. So what is being passed is 10. So 10 plus 10 and 5, so 25, and then returns q. It is returning the pointer value further, so it comes out. So what you get here is a pointer which is already incremented to 25. The value is already pointed to I only, but it is already incremented to 25. So we are again passing the pointer back again to the same function, and 25 plus 25, 50, 50 plus 5, 55 is again passed back. The pointer is passed back. Now the value is 55 now. It is getting passed to function 1, which is also accepting integer. So 55 is coming in, and then we are calling this. Maybe you have to be careful, I think. That means it is getting called again. Then 55 will come here, which will be 110 plus 5, 115. And that 115 is getting added twice. So 230 is the value. I think you guys have correctly found out. Okay. It's not difficult. So let us run it once on this, just to be sure that this code is running. Okay, so correct. Now I'm going to little bit make it little tougher. Some more problems are there which we'll see once now. Okay, this is going to explain you something else. Very good. So you are all already aware of it. Very good. So you are clear about row major, I think. That's the only crux of this problem. So even if somebody is not clear, maybe I will, for a completeness sake, I will tell you. What happens in C, they have decided, the C programming, when they are defining it, that the array will be stored in row major form. That is, row major, sorry. So when we have an array, suppose this is, suppose we have like this, only these two, suppose. I'm not saying about this array, some other array. Now these elements are, they have to be in a contiguous space, okay? They need to be in a contiguous memory starting from the address, whatever address the array is starting. Suppose you call it as A, it has to be in a contiguous space. Now every element might take 4 bytes, or maybe you may have an array of structures also. So the size of each element could be different. It could be based on what element of the character array or a integer array or float array. Each element could take n number of bytes. Assume in our case it is integer and we are running in a 32-bit mode. So 4 bytes. So each element can be stored in two ways, either row major or column major. Row major means we store the elements first taking the every row element in the contiguous space. Suppose we have 0, 0 is here, row, 0, 1, 0, 2, if suppose this. So you can have 0, 0, 0, 1, that element, this element, this we can follow this way, or we can store this one after this and then this column major. But here in C we are, the standard is to follow the row major. So it is going to store 5 2 means we have 5 rows and 2 columns, and it is storing it in the row major way. So this element, then this element, row major. So 0 1 2 3 4 5 6 7 8 9 are the values which are getting initialized. Now how are we getting it? We will see. We can get the address of this initial array is as IP, and we are getting I equal to 0, then till less than 10 we are going into the loop. Star IP is the first element which is getting the value 0, which is in I. Then we are incrementing both. So because it is following row major, the addresses will be increasing in this way. So it will fill this, then next address will be this element and this element. Now what is this IP plus plus is incrementing by 4 bytes. Remember, it is a size of integer. So it is incremented by 4 bytes and the next addresses are got, and we are initializing the array. And then 1 of 1 will be, this is 0, 1, this is 1, 1. So this will be, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So this will be 3, and 4 is this, 4, 1 is 9. So you guys are got it right, 3, 0, 3 and 9. And I am sure you are aware that we cannot do an increment of IARR. That pointer is fixed. We cannot, that's why I am getting the address into IP and then incrementing IP to initialize it. Otherwise, I have to do a indexed address for using the IARR. This address will never be changed. It is declared as a constant array, and that we cannot change it. Though it is returning a pointer, but we can get the pointer address to some other pointer and we can increment it. So that is allowed. Whereas you cannot increment IARR, AARR plus plus we cannot do. Okay. So I hope this is clear. Unless you have any doubts, we can go further. What we have to change is the code if we want to access the array in column major order. Okay, very good question. Okay, you want to, let me tell you, if you want to initialize it in column major order. Okay, let us try to do that. Maybe I will do it here. Why it's not going down? Okay, now what you want, let us do it. IP is there, which is pointing to the first address, this one, and then this is there, this there. Now you have to understand that this is stored in the row major form, that you cannot change. Okay, the order in which this array is stored is already decided. So let me write it there, 0, 0, 0, 1, 1 comma 0, 1 comma 1. This is how it is going to be stored, and where even if you want it, you cannot change it. But you want to access it in another way, we can do it. Now we have to jump. Okay, if you want to write a column measure form, you want to access it. You want to initialize it like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you have to skip some addresses and then keep increasing and then come back and again do it. Okay, I hope you are able to understand it. You have to do it this way only, or you can use an indexed way. You can use IARR and then access it in the column measure form. So how do you do it? Now that also you need to know that this is I. Suppose if I call this as I and variable j, this 1, 0, 1, 2, 3, 4, 5, and then this you can always keep it as 1. J equal to 1 you can keep, and then you can access it. So what you can do is IARR, you can put for loop, and then I you can increment it, keep that as 1 only. Sorry, I'm not able to show you properly. I hope you are able to get it what I'm saying. So this I variable for loop, you can put I equal to 0 to now in our case 4, okay, or 5, more than 5. This you keep on changing, but this you can fix it as 1, so that you are always 0 of 1 you are accessing, then 1 of 1, 2 of 1. So you can access it this way in that. Okay, so let us, do you want me to write it, or I think you can do it, but let me see whether you guys want it or not. Okay, increase the IP by column size. Yeah, you can do that. Column size, you can get it by getting the value. The problem is, again, you have to get back to this address. If you want, you are keen on filling this values also. Suppose the same way what we did, we want to initialize the array and then you want to come back to this address. You have to come back again and then do the same thing. Okay. Maybe what you can do is initialize the array initially 0 to 0 comma 1. Okay, 0 comma 0 you address you take, and then address of 0 of 1 you take, and then start incrementing it by column addresses. That also you can do. Okay, then it will be the what you skipping will be same. Okay, that also you can do. There are so many ways you can do. If you want to do it, make it easier, I would suggest that you use this way. Use the index and then increment the index only, so that you don't make mistakes, or even the reader will not be confused, because here it is not very intuitive. It is very, I written it like this intentionally, but please don't write your code like this in a production code, which will not be well appreciated. You will be scolded if you write such a code. Okay, in line 93. Okay, good. Okay, let me explain. See, in line 93, what we do, in star IP, it is getting the some address. Now you may wonder, what am I doing? Okay, let me tell you. In star. Now this always, when you have an array IARR of whatever size it may be, this is getting the address of the first element, which is 0 comma 0 of 0. Okay, this variable, if you are accessing it, this identifier or a variable, if you are accessing it just like that without any dereferencing or without any giving anything, you are actually getting the address of the first element of the array. Now why am I doing this typecast? Because this is a constant type. When you type, if you are writing a type of this, if you get the type of this IARR, it is a constant pointer. Okay. Okay, let me now const also. There are two things. Okay, I'm sorry. This Windows is a pain. Okay, Let me explain something more here. Const, okay, sorry, I will come back again. Int star IP. Suppose if I have, I can put const here or const here. Okay. When I put const here, it refers to the, now how do you read it? It is a, uh, it is called right left hand rule. Okay, right left hand rule. That means when you are having a variable IP, you are saying it's a const of a pointer type. Is a const, IP is a constant. Okay. Let me that I will explain it later. Okay, I need to give it to you with an example. Please don't. I will not give any const example now because I have not given written code also for it. I will explain it later. Right now, what I am saying is, remember one thing, that this is a array identifier which is having an address. It is having the address of the first element of the array, and it cannot be modified. I cannot do IARR plus plus or IARR plus 1 equal to some I. This I can do, but I cannot assign it to something. I cannot modify this value to something else. So IARR equal to IARR plus 1 I cannot do, or plus plus also is same. So I cannot do that. Okay. So I am doing a typecast of this to be, to make the compiler not to crib. I put int star here because this is not of type const. This variable IP address can be changed and it is not pointing to any constant value also. That I will explain later, maybe next class or something. So we are doing a typecast only for that purpose. If you are worried, confused why I am doing a typecast, because this is not allowed to be changed IARR, but IP can be changed. I am saying it is not of any constant type. So I am doing a typecast. And then I can modify the IP plus plus without any problem. Is that clear to you? You are right. Because we cannot change the base address of the array. That name of the array represents the address of the first element. That's what I said, 0, 0. Is that clear? What is this? Okay. You cannot, okay. Int star, can we just do, yeah, you cannot do this, okay. You can do IP equal to IARR, okay, ampersand you have put IARR of, where is the square, okay, 0. You can do this because you are right, IARR itself is an address. So we cannot, if you are doing a ampersand of that, in this case you cannot do it at all because there is no variable. Okay, let me see whether it is allowing or not. It might allow, but it will get the address of its variable where this IARR is stored. Okay, I hope you are clear. So you can element, you can get a first element and then take the address of that, you are allowed to do, or you can just do IARR. Okay, otherwise you are taking the address of that element itself if it is stored in a variable. Any other, sir? If we save the address of ARR into a variable and address of that variable is given to IP. Okay. What you are saying, let me write it. Let me keep your dialogues visible. So what you are saying is, suppose if I have int star IP, I hope we have this IARR already. Now IP is equal to, what are you saying? Okay, so IP is equal to IARR. Okay, and then if you are taking address of IP, then you will get the address of this value. If you want to access this array element, you have to say star star IP, because if you do this, if this type, okay, you are storing it here, and then if you are storing it into another variable, I will say pointer to pointer, and I have to declare it as star star. Okay, I hope this is clear. If you are taking the address of IP, which is already a pointer, then this type becomes int star star. So you have to say int star star IPP equal to ampersand of IP. Okay. Okay. Oh, okay. Now this will not allow you. Okay. A strict compiler will not allow you because there is a type mismatch. But you can do it. Address of AAR. See, even that address of IAR, what becomes is it becomes an integer pointer to pointer. But this type is little array type, but you cannot assign it to an integer. You have to do a typecast. And then you should be unsigned int. Please remember. Okay. One more thing I will tell you. Suppose if you are saying integer a, okay, it's an integer variable. Integer variable means it's a signed variable. Normally, what happens is when you are declaring an integer, what happens is there is a um, convention that you have to say signed int. Okay, then you are specifically saying my integer is a signed int or unsigned int, and you. I am just giving a name so that we are not getting confused. So if you do not mention it, most of the time the compiler assumes that it is a signed integer. That means if it is a integer is suppose 8 bit wide integer, then it will be from 0 to 254, sorry, 55. Okay, it is 0 to 255 is the value, total value, right? 8 bit. So if it is a signed integer of 8 bit value, then it will be 0 is here, 127 is here, minus 128 is there. So it will be between these two values. Okay, if it is a signed value. Now there is a lot many things I need to talk about. We will take it up maybe in the next lab about signed integer and unsigned integer and how it is handled internally, because there are some confusions I have noticed in the interviews when I talk to people. Let me explain here one thing. If you are just saying integer a, it is assumed to be signed int. Now, what is the problem in assigning an address to the integer? Let me explain that. Where I started off there, but I am going somewhere. Suppose int a you have declared, and then you are assigning an address of maybe this. Let us assume you are properly taking it. We are taking the address of this first element and assigning it to an integer. The problem is this is considered to be a signed value. So, but always remember the addresses are unsigned. They are unsigned. You are allowed to do arithmetic, but they are treated as an unsigned integer. When I say unsigned integer, suppose if you have a 8-bit value, suppose you assume that the machine is a 8-bit microcontroller and all your pointers are of 8-bit wide, okay, assume that, then all ones, okay, which is FF in hexadecimal, is considered to be a positive value, okay, positive value. So this FF corresponds to 255. Whereas if it is considered as a signed integer, then it will take this as a negative value because the MSB of this 8-bit is set. So this will be considered to be as, if it is signed int, then it will consider this value to be a negative value because it is no longer 255, it is a negative value. Now what is that negative value? How does it compute? That is the 2's complement. All of you might have studied. Now remember, this is not I, it is E. Okay, common mistake is write complement. I give you compliment means I appreciate you. A complement means reverse. Okay, in a 2's complement, that is the binary operation. Now remember one thing, all the signed values in all the machines, most of the machines, or almost all the arithmetic are done in 2's complement form. The signed integer values are represented as 2's complement. So what does it mean? If this number, I am treating it as a signed number, then MSB is a sign bit. Okay, MSB is considered to be a sign bit, and if it happens to be a signed value, then it has to be a negative value. Now you don't know what is this negative value. So to do that, you have to find a 2's complement of this. Now when you do a 2's complement, all of you may be knowing it, I'm sure. I'm just considering 8-bit for easy thing. Okay, the same logic holds good for 16-bit or 32-bit also. So if this considered to be a signed value, then what we do? We do a 2's complement. Now how do you compute the 2's complement? First, inverse the bits, inverse all bits, and then add +1 to it. Okay, that's what we do. Now 2's complement means we say inverse all bit 0 0 0 0, and then we consider it to be +1, so it will be 1. Now this all ff will be considered to be -1. Okay, minus value is taken from the sign bit, and then you complement it and add 1, so it will be considered to be a -1. So in the representation, 0 is there, 127 plus is there, minus here -128, and then it goes up to -1. Okay, so this is the last value. This is how it is represented. So one, you get 1 less. Now what is the value of, let me tell you, normally people will get confused with this value. Suppose if you have a 1 0 0 0 0 0, okay, what is the value of this pattern? What is the value of this pattern, assuming that this is a signed number? Okay, no. Anyone else? What is the value of this? When I find, what is the value represented by this? Very good. Tanmay is correct. Now I will tell you, this is a very confusing thing. The same logic I am going to do. Okay, I am going to complement the bit. Okay, I did all 1 1 1, I complemented and added 1, I got -1, right? This value I got. Now I will do the same thing. Now I will complement this. All bits are complemented, so it will become 0, and this is 1, this is 1 1, and then I have to add 1 now. Now what happens? This is 0, carry 1 plus 1, again 0. Assume that these are all zeros. Okay, I am not showing it, all of 0. So you get a carry always. So you get 0 0 0, and then there is a carry here also. So this also is 0, 4 are there, 3 are there, and then this one gets a carry here, and that comes here, and 1. You get back the same value what you started off with, which is actually representing 128, but now it is, because you are representing at a signed bit, this is -128. Okay, this value is -128. What Tanmay said is correct. This is the most confusing part of this 2's complement. Okay, I hope this is clear. Okay, you have to play around with this. In C, you are likely to make mistakes if you are doing a signed and unsigned integers and comparing the addresses. Okay, so you have to be very careful when you are handling it. So, and most importantly, we started off with something. All the pointers are to be treated as unsigned integer. So first thing, whatever Anand Jain said, you cannot assign it to an integer because it's a signed integer normally. It should have been unsigned. Why I am, okay, let me explain why I am saying that pointers have to be unsigned. Okay, remember, the pointer addresses do not have anything to do with the signed arithmetic. Remember, They are all, even if suppose if I have an address called F000, this is an address 0x F000. That means what? I am saying that all ones, 000 and all zeros. That doesn't mean because this MSB is set, I don't say that it's a negative address. Addresses cannot be negative. Remember. So if I am having a 8-bit address, I can represent from 00 to FF, right? I can represent all 256 locations starting from 00 to FF in the sequential way. I am not associating anything to do with the MSB bit as signed value or unsigned value. I am not treating it as a signed bit. I am treating it as a unsigned value. So the MSB bit is not treated like a signed bit. That is a significance of treating something as an unsigned value. That means the signed bit will not be considered to be the MSB bit will not be considered to be a signed bit. So when it is doing arithmetic, the ALU does something. Okay, I will spend some time because when I am recruiting people for DSP team, I found that the engineers with 4 or 5 years of experience also did not have a clarity on the following flags. I know I will ask you to think about it. You might have studied in your microprocessor course 4 flags you might have studied. CN O, yes, okay, I am not writing it in a proper way. Z, okay, Z, P, okay, CNZP. Okay, CNZP is the standard ARM thing. This is okay. Overflow is V actually. CNZV. Okay, sorry, CNZV. Okay, let me say CNZV. C is a carry flag. N is a negative flag, which is nothing but the MSB bit of any value. 0 flag is the value, the whole value 0 or not. V is the overflow flag. So what is the difference between carry flag and overflow flag? Okay, it goes back to the basic binary arithmetic what you have studied in your digital design courses. Maybe I will take it up maybe in the next class, but you guys can tell me what is the difference between a carry flag and overflow flag. You can also Google it and study, or I will explain later. Okay. Yeah, Shubham, one overflow MSB. No. Unfortunately, it is no. Okay. Shall we take it up now? Okay, why should I defer it? Okay, let me take it up now. Because this is a standard question I ask normally. Let me take a 4-bit ALU. Okay, 4-bit ALU. R of EX, R of carry in and carry out means overflow. R of carry in and carry out means overflow. Not really. Oh, X. What is that? XR. Okay, very good. Yeah. So let me tell you. You guys do it. Okay. Otherwise, we'll be going into that. I will explain you something. Okay. I call it this as a carry 1. Suppose if I call this as a carry 1 and this as a carry 2. Okay. If I call the okay, I'm talking about 4-bit ALU. I am not telling you what I am adding. Okay. I will defer it maybe for discussion later. I call this carry as carry 1. I call this as a carry 2. Okay. Then C1 XOR of C2 sets the overflow flag. C2 sets the carry flag. Okay, carry flag. This is overflow flag. This is carry flag. And suppose the result I am getting it. Okay, I am getting some result x1, x2, some x3, x4, something. If all these bits are 0, all are 0, then 0 flag is set. Now, which is set left now? Sign flag, sign bit. Sign bit is set. Suppose if I call the result is some 1 0 1 0. Okay, I'm not adding it or anything. Suppose this is 1 0 1 0. This bit, whatever MSB bit of the result, is the sign flag. Okay, so sign flag, zero flag, very clear, straightforward. And this carry coming out of the 4-bit addition is C2 is carry flag, the value whatever is coming, whereas overflow flag is XOR of C1 and C2 is overflow flag. I will leave it with that. And yeah, that is what you are calling C in and C out. Okay, you are calling this as a C in maybe, C out. Okay, yeah. So can you tell me why is it so, and what is the overflow flag signifies, and what is the carry flag signifies? What is the difference between OV and C? Okay, we will break now. We are almost 1 hour. Shall we break? We'll take. You can Google it by now. I don't mind, even Google it, no problem. We will have a 10 minutes break now. You can come back, or we can discuss something else. I will continue with the C programming maybe after the break. This I will keep it as a exercise for you. Overflow flag is to indicate that the number is exceeded the upper limit. Upper limit of what? Then what does the carry flag signify then? If overflow flag is indicating that it has reached the upper limit, it cannot be packed into the given 4-bit, then what does the carry flag mean? What is the difference between them? Okay guys, I will defer the break for another 10 minutes. Is it okay? We will complete this discussion because you are all in the thing. So let us do that. Okay, because I started off with an okay, fine. Now let me tell you. Okay, let us talk about 4-bit ALU. Okay, keep your mind in the 4-bit value. Okay, we are not talking about, when I say 4-bit ALU means the ALU takes only 4 bits in, 4 bit out, and the result is also 4-bit. Okay, anything coming out of 4-bit is a problem. We cannot handle the results beyond 4-bit. Okay, now if it is a 4-bit, what is the maximum things we can represent? I'm sure all of you know. So 0 to 15. Okay, correct. 16 values can be represented. Now again we bring in the signed and unsigned arithmetic now. Okay, bring in signed and unsigned arithmetic. Now in a unsigned representation, we can represent from 0 to 15 because we are not considering the MSB bit as sign bit. We are treating it as a value. So it is changing from 0 0 to all ones. We say 2 power 0, 2 power 1, 2 power 2, 2 power 3. So what is that? 8 plus 4 plus 2 plus 0, sorry, 1 is 15. Fine. So this is 8421 coding. So 12 plus 13 plus 14. Sorry, what is that? I am not adding or what? Is it correct? Yeah, correct. 14 plus 1, 15. Okay. Now let me say, if you are doing an arithmetic, okay, you can, if you want to represent as signed values in this, then what we will do, let me write it fully, then we will see clearly what it means. Please correct me if I am making any mistake. Okay, I have to go on for 4-bit is too much for me. Okay, now I represented, and I have to do the same thing, mirror image of this, not mirror image, it's not a mirror image, it has to be 1001, all that. Now let me take one example. Okay, suppose 0 1 0, okay, 1 1 0 0. Okay, let us go like this. Okay, I want to add these two numbers. Now, what do they represent? What is the value they represent? Okay, let me find something else. Okay, yeah, this will not be a good thing. Okay, it's fine. What do they represent? If it is an unsigned value, what it is representing, and if it is a signed value, what is it representing? So let me call it as unsigned representation and then signed representation. Now this value in unsigned, what does it mean? In signed representation, what does it mean? Now in this is 2 power 0, 2 power 1, 2 power 2, 2 power 3. So 8 plus 2, 10. Okay, this is 10 here. This is 12 here. What about these two values? What are the values? If I say that this is a signed value, I am talking about only 4-bit. Okay, our CPU is only 4-bit. Minus 6. Okay, so let me take this guy 1 0 1 0. I have to complement it 0 1 0 1. I have to add 2's complement. So 0 1. This there is a carry 1. There is no carry. So 1 0. You are right. So this is 6. Because I did a 2's complement, it is minus 6. What about the other guy? This guy. This will be 1 1 0 0. So 0 0 complement it 1 1 plus 1 you do. So this 0 1 0 0. So minus 4. This is minus 4 and this is minus 6. Correct? Very good. Now let us, okay, what happens in a CPU? Okay, let me explain. Hardware, what does it do? The hardware, what the adder, full adder, you might have studied full adder. Okay, it does not bother about whether what the bit pattern sent to it are signed or unsigned. The CPU inside digital design circuitry does not bother. Okay, it is the software at level we are considering it to be a signed or unsigned, but hardware treats it as a bit pattern. Okay, so let us, okay, now let me write it as minus 6 here, minus 4 there. Okay, now let us do a our arithmetic on decimal. We'll do arithmetic, and then binary arithmetic we'll do. This is how much it is, minus 12. You correct, no? Or minus 10, right? I am very poor in doing the decimal arithmetic. Binary arithmetic I am good. Okay, minus 10. This fellow is 22, right? Now if unsigned arithmetic is being done, it should give a overflow for sure. What about signed arithmetic? Is it overflow on signed arithmetic also in this case? This is also cannot be represented. Both ways it is not a good thing. I didn't take a proper number. Fine, now no problem. Let us do addition and then I will explain you the flags and then what happens to the flag. Okay. Now let us add this number 0, 1. Normal binary arithmetic addition you do. This is 1. This 1 plus 1 is 0. 1 carry is going, which is 1, and this 1 is coming here. Now this 22 corresponds to what? Suppose you had a 5-bit ALU, suppose 5-bit, suppose if it was a 5-bit ALU, then you would have got this 1 as a valid address. So you assume that this value is a 5-bit value, then what will happen? This is 2 power 0, 1, 2, 3, this is 4. So this is 16 plus 4 plus 2, which is equal to 22, correct? So if it was a 5-bit value, it would have been a correct result. But because we have assumed that this is a 4-bit ALU, this carry which came out is going to sit on a carry flag. It is going to be setting a carry flag. So in decimal, in a hardware, there will be a carry flag, a flip-flop will be there. It will set that value. So it becomes 1. Carry flag will be 1 when this arithmetic is done. Okay. It is clear, and it is also clear that 22 cannot be represented in 4-bit. So carry flag being set means that unsigned arithmetic, there is a overflow. Carry flag means there is a overflow when you do the unsigned arithmetic. Now what is the situation in signed arithmetic? If you assumed these values which you are adding were signed values, then you will also assume the result also a signed value. Remember that. Okay, it is the assumption that the software guys make based on the results what we get. Now what we got 0 1 1 0 is the result we got. If this bit is set, that means this is a positive value. Whereas what we added was -6 and -4, and we wanted -10 to be there, and we got a 0 which is a positive value. So it is a error. Okay. Now let us come back to, hope I am not lost you. Let us assume that now we are having a 5-bit ALU. Okay. We were having a, now assume that 5-bit ALU. In that case, this addition would have been treated as a positive value. Okay. Because this is 0 and this is also 0, we are adding it, it would have been considered to be a positive value which is becoming a negative value. So that is also error, that overflow is there even when if it is a 5-bit value. But let us not consider it to be a 5-bit value now. I will stop here, and then I will tell you how this, we have to find out that this result is a erroneous result. Okay, you should have got a negative value here, but we are not able to get it. We are not able to represent a signed value within the 4-bit value. How will you find out? Now trace back the carries that you got. Now let us do the addition again. Okay, because I am doing too many things there. So let me do an addition without making changes in the value. I am doing the same addition. Okay, I have not changed the value yet. I am assuming it is a 4-bit ALU only. I am adding the value 0 1 1 0 1. So there was a carry here, but there is no carry here. This was 0 and this is 1. This is, I said that this is carry 1. If I call it as carry 1 and carry 2, I will say carry 1 XOR carry 2 is equal to overflow flag, I said. Now C1 is 0, XOR of 0 and 1, C2 is 1, 0 and 1 is 1. So overflow flag is set. Overflow flag indicates that the signed arithmetic performed in this addition has also resulted in an overflow. That means this addition is wrong both for signed as well as unsigned, because you know here -10 cannot be represented in 4-bit, 22 also cannot be represented in 4-bit. So both are wrong. In this case, carry flag will also be set, overflow flag will also be set, and both are erroneous. With the 4-bit ALU, we cannot perform. Is it clear now? So far, now I will explain you with another example so that you understand when overflow flag is not set. Okay. Now suppose 1 0 1 0 1 0 0 1. Okay. Let us do whether this arithmetic, what is it resulted. Now this 1 0 1 0 will be in negative minus signs sign number. What will be the value of this? Complement it 101, which will be 4 plus 1 5. This is -6. This is complement 110 plus 1 7 -7. So this is also not a good idea. So no, I should get something else. Let me do one thing. 1 0 1 0 1. I want to take two negative values. Okay. Okay. What is this value? This is also not a good value. So let me do one thing. 1 1 1 0. Okay, 1 1 1 0. All 1 1 0 you do it. Okay. What is this value? 1 1 0 0. This is -2. This also -2 results in -4. You are right. Right. This, let us take this value. Okay. Now 1 1 1 0 1 1 1 0. This is -2. This is also -2 -4. Minus 4 is a valid representation in the sign bit representation. So let us add now. We get 0 here. 1 plus 1, 0. You get a carry here, 1. This is resulting in 1 because 1 plus 1 plus 1 is 1, 1, 3. So 1 is here and one more carry goes here. This also results in 1 and then 1 carry goes here. Okay. So C1 is equal to this. C2 is equal to this. Okay, sorry. C2 is equal to 1. Now, as I mentioned, C1 XOR C2 is 1 XOR this is 0. That means overflow flag says that there is no overflow as far as signed arithmetic is concerned. That means this value, whatever is a negative value represented, is valid. That means 1100, if you convert it into a, if you want to know the positive of this value, what does this actually represent? It will be 0011 plus 1, which is nothing but 0100, which is minus 4. So minus 2 plus minus 2 result in minus 4 is a valid arithmetic in signed arithmetic. So, and overflow also says correctly. Is it clear now? The overflow flag indicates signed overflow, whereas carry flag indicates unsigned overflow. So here what happens? C2 is same as carry flag. Okay. So that is 1. That if it was represented as, if it is need to be represented as a unsigned value, it is a overflow because 1110 is what? It is 8 plus 4 plus 2, right? 14. So if you add 14 plus 14, 28 is the overflow. So what you got is not a valid value because if you represent this also as a signed unsigned value, it is 8 plus 4, 12. It says 12, which is not valid. So as a summary, what is the doubt? Okay, you are adding these two number, or I didn't get you. Last two, okay. These two, okay, correct. Okay, let us do it. One, sorry, working, sir. Okay, fine. For others understanding, let us do that. 1001 1111. Okay. Now, what do you get it? You can actually do a arithmetic and then find out what flag is set. 110. You are getting and carry flag here. This is 0. Oh, sorry. Yeah, 0. And you get a carry flag 0. You get a carry flag 1. So 1, and then carry flag is set. Okay, carry flag is set. Now overflow flag is set or not? Overflow flag is not set. Okay, because there are carry here also, here also. 2 carries are there. So overflow flag is not set. In our case, overflow is 0, carry flag is 1. So let us see whether it is true or not. This value is supposed to be minus 7, right? You know that. Because if you add 0 all once and then plus 1, sorry, minus 8. Sorry, minus 8. Okay, this is minus 8. Now, what are you adding here? You know that 0, 1, 1, 0 plus 1. So it is 7. You are adding 7, minus 7. And then this all zeros and 1, minus 1. So if you are adding minus 7 and minus 8, minus 8. So this is correct. Overflow flag is correct. Value is correct. And carry flag is also correct because carry flag is not correct. Unsigned arithmetic is a overflow. Is it clear now? Okay. I hope I got 10 minutes break. Shall we take? What do you guys, what do you want? You want early break, early going off early, or you want a break? I am open for both. Early is better. I don't know if anybody says break. Mayank said break. So always somebody saying break gets a higher priority. Okay. So break. Sorry. Please wait for 10 more minutes in the end of the class. So let us break now. What is the time? If you want, you can have a short break if you are okay. Instead of 10 minutes, we can have a short break also. I am fine. So let us meet at in between 9:20. 7:20 we'll meet. So that we are meeting. Is it okay? 7:30 is too early. Okay. I'm not showing my face. You guys don't know whether I am there or not. I hope this is clear. Now I have not connected the dots actually. I told you two things, okay? In fact, two things, three things maybe. I said in C programming, we said we have to either mention whether integer is a signed integer or arithmetic unsigned integer. So I will tell you what happens internally, okay? Unsigned u, and then I also told you the arithmetic whatever happens is the problem with the software, right? Now let me explain that little bit more what exactly is happening. I explained about the hardware. Hardware, what does it do? Suppose if you are adding two numbers, it is just performing the addition and then leave the overflow flag state something and carry flag it leaves some state, okay, after the ALU arithmetic has been done. And hardware does not know whether it is adding two numbers n1 and n2, whether they are both are signed or unsigned, it doesn't know. One thing you remember, mixing the signed and unsigned numbers in the arithmetic is normally frowned upon. It's not accepted actually. Better not to do that, okay? Unless you are very specific and you know you are aware of what you are doing. Now, suppose you have an integer you are declared, which is a signed integer and unsigned integer, and then you start doing arithmetic between them, and then you may compare the results of R1 some result and then R2 you are comparing, okay? Now, when these things are happening in the software world, you are having a clarity whether the value what you are doing is unsigned or signed, because you have declared properly and then assume that the software is managing it properly. Then you may wonder how the hardware which is performing the addition and then leaving the results here is mapped to the software. That is where the assembly instructions and the specific flags being checked is coming, okay? Now let me explain what I mean by that. Suppose you assume you are comparing, you are doing a signed arithmetic, okay? S1 and S2 are some signed integer and you are doing minus of this, and then you want to check whether it is greater than some value k, okay? This is if you are put, okay? Now this is some value k. When you do this, it is assuming that this is a signed arithmetic because you are declared S1 and S2 are signed, and then you are comparing this also signed because you are comparing two things, means it has to be both are same type, so signed integers, you are comparing them. Now internally the architecture, what does it do and how does the compiler convert this? Compiler takes care of throwing up some assembly instructions, proper assembly instructions according to whether you are doing a signed arithmetic or unsigned arithmetic, as well as whether checking proper flags, whether it is supposed to check overflow flag or is it expected to check carry flag. That is decided by the compiler, okay? If you are writing it in assembly, you have to take care of yourself because you should know what value you are doing. Otherwise, compiler is aware of this thing. Suppose if you are saying unsigned number u1 is greater than u2, then you are doing an unsigned comparison. So it will generate the assembly instructions and then it will check the carry flag for validating carry flag, okay? Carry flag it will check. Now what does it do when you are doing a less than or greater than? Normally this is converted into a compare instruction. Compare instruction in assembly of R1 comma R2, if you do, what happens is compare does the subtraction R1 minus R2, okay? It will do compare will do a subtraction and it will affect the flags. The flags in the processor are affected. Affected means they are modified. CZNV is modified. And then after the compare instruction, the values of R1 and R2 remain the same, okay? Most of the architectures do not disturb the values of R1 and R2, but because here in your if comparison you are saying u1 is greater than u2. If you want to do this comparison of whether one number is greater than or less than something, it has to be subtracted and the flags have to be reflected and proper flag should have been checked. Now if else, if you do, if you are doing if else, then based on this comparison you will enter this instruction or this instruction. So that will correspond to some jump on overflow or jump on carry. These are the instructions which will be generated based on whether you are doing a signed arithmetic comparison, signed variable comparison, or unsigned comparison. If it is unsigned, it will throw up this instruction after the compare, jump and overflow. That means it will check the overflow flag. This flag it will check. If it is jump and carry, it will check this flag. So based on whether you are using what type of variable, the compiler takes care of either generating this code, jump on carry code or jump on overflow code after performing the comparison. Okay, this is how the instructions are generated by the compiler. So compiler needs to be informed whether the variables are of what type, and programmer, as a programmer, you should also know whether you are handling the variables properly or not. Okay, so this is how internally compiler does. And if you are writing assembly code, you have to take care what value you are putting it inside R1 and R2, whether you are having a signed value or unsigned value. Even the registers or the processor does not care whether you are carrying an address inside the register or you are carrying some signed value inside a register. Nobody knows. That's why when you do pointer arithmetic, suppose if you are comparing two pointers p1 and p2 greater than or equal to, then compiler knows that the p1 pointer, suppose int star p1 int star p2, then default, if you are doing p1 is greater than p2, then compiler knows that you are trying to compare p1 and p2. This p1 pointer address and p2 pointer addresses would have been in some register r1 and r2, maybe some r4 and r5. Don't assume that it needs to be same. So when it is comparing cmp r4 comma r5, it knows that it is performing a unsigned unsigned values. It is comparing unsigned values, so it is performing a subtraction of unsigned values. So it should check for overflow, not the overflow flag. It should check for carry flag. Okay, because this is unsigned. So that compiler is aware of. Okay, that's why I am saying that you need to be very careful when you are dealing with all this. Please do one thing as an exercise. Try to declare some C variables as signed integer, unsigned integer, multiple values u1, u2, u3, i1, i2, i3, and then initialize it with some negative value, positive values, bigger value, because assuming that it is a 32-bit processor. Okay, make sure that it is a 32-bit integers, and try to perform additions, comparisons, and get clear about what are the values. Okay, that will make you a clear, very good embedded programmers. Okay, I hope this is clear. Shall we move forward? I will move forward, and unless you have any doubts, please ask me always in the next class or even during the thing. Okay, now let us go to another question. Okay, I'm sorry, I want to only show you that. Okay, please go ahead. So this is not very difficult. We are starting with SI as 1, VI as 2 is volatile. Okay, I will talk about volatile maybe later if you are because of the time constraint. We'll complete the questions now. I have so more things to do. So SI plus plus will make it 2, VI plus plus will make it 3, I plus plus, CI we cannot change it, so I plus plus will make it 5, and then what do you do? VI plus SI plus VI plus CI plus I. So 5 plus 3, 8, 8 plus 2, 10 plus 3, 13. This is 13. So this whole thing is 13, which is written into I also, VI also, SI also. So now all of them becoming 13, VI and I, it becomes 13. Now what is getting printed? Remember, printf, whatever you have, a, b, c, I think I mentioned it in the last class, parameters are pushed into the stack from right to left. Okay, this is this. Now doesn't matter, it is getting printed. Now this is how it is processed. Okay, when I say you should comma parameter, comma operator, okay, it's not a parameter, comma operator is the least priority precedence in the whole game, and it is actually getting processed in this order. Okay, right to left. Now because there is no dependency, a side effect is not there in any of the, I think we can call it as a side effect because it is modifying the variable while passing the parameter. So it is a side effect is there in this case, but there is no effect between the parameters. So it doesn't matter whether you are getting processed right to left or left to right. This doesn't have a impact because we are not using the same variable in multiple places. Okay, in that case, that awareness is required that it is getting pushed, but the compiler might do it in a different order. We don't know. We are not depending on that. Now, forget about the order in which they are pushed. Now, SI is going to be 13. It is correct. VI plus plus. Now, plus plus is a pre-index, post-index. This is a post-index. That means the VI value is pushed into the stack and then incremented. So, VI is currently 13, which is incremented and pushed and then incremented. So it will be 13. CI is same value, whatever is there, 4 or no, CI is 3. So CI will be same. But I plus plus, what happens is it is incremented first and then pushed into the function. So it was 13. So it becomes 14 when it gets printed because the incremented value is also, what is pushed into the stack. So I think most of you got it. Okay. If there was a CII plus plus, yes, it will give an error saying that it's a constant variable which cannot be incremented. Okay, that is what you will get. Now, I put a volatile here, but I don't know how many of you are aware of the difference between the volatile. I want to show it with an example. Maybe we will defer that for a while. We will not go into the details of volatile. It involves some more thing I want to explain very clearly there. So we will defer that constant and volatile for the later discussion. Okay. So I think so far there is no doubt and you are all got it correct. Maybe by some mistake initially you had and then you have corrected it. So no problem. Now little bit interesting stuff is coming. I want you to be careful. Okay. Okay. Now, what do you understand from this? You cannot guess the output, okay, for sure. But I want you to tell me if you get this true or false, what does it mean? Or will you get always one value or different value? You can tell me both. Okay. In the interest of time, let me explain what is being done here. Okay. Union, I'm sure all of you may have the theory behind it. Okay. Now, union, the size of union is always the greatest size of element in it. Okay, whatever is the size. Now suppose if I have a union of some x, I have a float f double d, then this 8 bytes, this is 4 bytes. So the size of union is 8 bytes. It will always, it is not the sum of these two. Okay, it will not be sum of 4 plus 8, 12 bytes. It will not be reserving like that is like a structure. If it is a structure, it will do allocation for each of them and then it will be sum of that. But what does the union do? It is combining the location reserved for each variable in the union to be the same memory. Okay, but since you are having float and double, it will allocate 8 bytes for this. If it was a double, it will take 8 bytes. If it is only float, it will take only 4 bytes. Now what does it mean? Suppose if I am declaring it as a x and x dot f equal to 1.2, then this 1.2 value what I have loaded will sit in this place, in this memory. Okay. Whereas if I say x dot d equal to 1.2, now this is a double representation, 8 byte representation of 1.2. So it will occupy all the 8 bytes, and then you have to read it as all the 8 bytes to understand 1.2. If you store it as x dot to d 1.2 and then read it as f, it will not be correct. Okay, let me explain what I mean by that. Suppose I am just explaining this union, which is x having float f and d double, and then I am doing x dot f is equal to 1.2, and then next I am doing x dot d is equal to 1.2, then printf percentage f, okay, x dot f. Now I am accessing x dot f after assigning x dot d. That means I have taken all the 8 bytes to represent my 1.2 in the double format. Double format is totally different from the bit pattern is different. Okay, so it is occupying all the 8 bytes of the value, and then it has filled the pattern for 1.2, which is in the double representation, 64-bit representation. Whereas when I am printing it, I am accessing it as x dot f. Because union accommodates both the variable in the same memory, you are only normally it will be the lower value 4 bytes. It will take this bit pattern and then try to interpret it as a floating point number, which will not be correct. It may be some number. Okay, it may not be what you have expected, what you are expecting. Don't think that you will get this value. You will never get it. Yeah, I want you to try it out. You will not get this value because you are initializing it with the bit pattern which is meant for double, and then trying to read it as 4 byte value, for 32-bit value. It will be different. Okay, this you have to understand what is happening. Now this is totally a different explanation. Now what is happening in this particular program here is I am saying 0x55ff, which is in binary form. 55, you know that it is this is 55, right? This is 5, this is 5. FFF is 11111. Now I am accessing usc.s short form. That means I am storing this whole thing. Okay, this is 1 byte, this is 1 byte, this is another byte. I am storing it in the USC structure. Okay, after that I am having 0 and 1 is a character array. That means if this is the starting address of this union, that will be fixed. This is the 0th element and this is the second element of C. C is 0, C 1. Now I am comparing if CSC of 1 is equal to 5. That means if this value is here and FF was here, then I am printing true. If the other way, it is false. What does it mean? If you have come across big Indian and little Indian, I am sure you might have. Now, if I have a 16-bit value, similar thing what I am having, 0x55 is here, FFF is here. Okay. If this machine that I am running on If it is following a big Indian NAS, okay, then in a given address means this USC structure is in some address starting from maybe instead of this I will store it like byte address. 2 bytes are there. This is address some 100, 101. This is 1 byte. This is width is 8 bits. Okay. Now this USC union is starting at this address. Assume that means what? My C of 0 will be here. C of 1 will be here. This location, this location. If my machine is following a big Indian NAS, then the bigger value, the higher, see, not in terms of the content, it is in terms of the value, in terms of this is 2 power 15, this is 2 power 0, this is 2 power 7, this is 2 power 8. So in terms of value, this is big, right? It is carrying the bigger value of this 16-bit thing. Big Indian NAS will keep the MSB part of it in the lower address. So 55 will sit in this and FF will sit in this place if it is a big Indian machine. Yeah, okay. If it is a little Indian machine, okay, if it is a little Indian, it will store the lower part in the this address 100. So FF will be here, 55 will be here, 101 will be here. That means C of 0 will be this, C of 1 will be this. Now what I am comparing, USC of 1 I am comparing with 55 if it is true. That means little Indian is true if I am getting true. Little Indian is false in this case. Little Indian is false, then it is false. That means it is a big Indian. So now where I am running this program on, I am running it on Intel machine. Okay, Intel I core 7 whatever. So this Intel machines follow little endianness. Okay, earlier Motorola processors, Motorola had big endianness, whereas ARM has a programmable endianness. Suppose ARM can be programmed to be little endian or it can be programmed to be big endian. When do you do the programming? It's not that when you are running a software, you will decide that, oh, I want this ARM processor to be a little endian. For this process, I want process P1, I want it is a little endian. For process P2, I want big endian. It is not possible. The processor has to be, when it is booting up, first some configuration bit has to be set to say that this ARM processor is going to behave like a big endian machine or little endian machine. Now, once it is decided, what happens is, suppose you have a register, 16-bit value register. I have stored the same 55FF. When it is writing into the memory, it will make sure whether it is behaving like supposed to behave like a little Indian machine or a big Indian machine. And then if it is little Indian machine, whatever is the content of lower value, it will put it in the address, first byte of the address, and then the next value it will put it here, writing. Similarly, while reading also, it knows that it is a little Indian machine. So when it is reading two values in a contiguous memory, the first lower byte will be moved into this lower value and the higher will be moved into this value. Whereas if it is programmed as a big Indian, it will do the reverse of that. That is how this big Indian and little Indianness works. So in this case, you will get a different output based on which processor you are running on, whether that processor is programmed to be a big Indian machine or a little Indian machine. Okay, so it is what happens in the 32-bit value. Okay, if suppose you are having a 32-bit value, now there are 4 bytes. Let me call this as a byte 0, byte 1, byte 2, byte 3. This is in some register R5. Okay, a 32-bit register. Each bytes are there. Some value is there. Okay, Let me call it as AA, BB, CC, DD. Those are hexadecimal values. If it is a little Indian machine, and if this value is supposed to be written into the address 100, that means 100 is the address, 101 is another byte, 102 is another byte, 103 is another byte. Now, if it is a little Indian machine, DD will come, CC will come here, BB will come here, and AA will come here. If it is a big Indian machine, big Indian, okay, AA will come here, BB will come here, CC will come here, and DD will come here. It will be, the processor will send it like that. So if it is a Intel machine, it's a little Indian, it will always send the DD first, then CC in the next addresses. Okay, you know that 32-bit value takes 4 bytes in the memory, but you have a freedom to store those 4-byte values which you are transferring from the register to the memory in 2 ways. You can store it in this way or this way. That's why there are 2 ways of storing it in the memory. And this program tries to find out whether the processor is in big Indian machine or a little Indian machine by running this code. I hope this is clear. Any doubts on this? Very good. In networking, okay, very good question. Actually, you made me say something. Okay. Yeah, you are right. Okay, Sandeep. Okay, because this is a 2 bytes, it will be stored in guess, and if numbers are stored in big Indian format. Okay, I hope this is I don't have to answer now. This, let me answer this. This is called network byte order. Okay, network byte order. Okay, now let me give you little bit of history. When you have a IP header, if you have seen IP header, okay, IP header has a type. Okay, this is a 32-bit value. Okay, this is 32-bit value. Okay, and this has a, whether it is 4 or 6 is there in the this particular 4-bit, because they need to know when they are getting IP header itself. Okay, whether how to how to interpret the remaining bits. Okay, whether we have to consider it to be a IPv6 header or IPv4 header, it has to be interpreted properly. Okay, so it is based on this type. They have decided that either this value will be having a 4 or 6, the first nibble, and based on that it will be interpreted. Okay, and one more thing, class A, class B addresses, if you have noticed, class A IP address, class B IP address, class C IP address, this bit pattern 1100 or 1110 or 100, they represent whether the address, the beginning address, okay, MSB portion of the IPv4 address, okay, represent whether this is a class A address or class B address or class C address. Okay, this top portion gives you. After that, you have a subnet and other things you will be doing it. Subnet masking you will do, and then find out the host and the network address. But the first one nibble gives you that. So when it is in memory or when it is received, okay, when it is getting received in the packet, you can see that they have to send this information first. Okay, when it is going in the network, okay, packets are getting received, okay, byte by byte. They have to, when the 32-bit value is there, they need to send it in some order, so that what is being received is the higher portion of the values. That's why it is a big endian in network byte order. Okay, just before I make a statement, I also want to verify network Okay, it is already there coming as a big endian. I wanted to be sure. Multi-byte order, network byte order is a big endian. Okay, that's what I said. Network byte order is a big endian because they want the higher nibble values, both in terms of even in the IP header also has that information, and even the class IP address itself, destination source or IP address or source for IP address, they have the information on the higher side, whether it's a class A or class B address. So having the higher byte coming first in the network is important. That's why when it is sent on the network, it is in the big endian order. Okay, network byte order they call, because higher byte values are sent first. Why? That is one reason. Another reason is there should be a uniform transmission of things. Suppose this is a Intel machine. Okay, I am running Intel machine here. I am running a Motorola machine here. Okay, or maybe ARM with a big endian ness here and little endian here. See, a processor CPU can follow any one of the endianness because they are only storing it in their memory and they are only reading it from the memory. Okay, who is storing it, who is reading it, they are same. But if multiple processors are involved, suppose you have another processor also reading it and writing the common thing, they should follow the same convention. Otherwise, one processor following little endianness and another processor following big endian, they get confused because one will be writing in some order and other fellow will be interpreting it in a different order. So if you are having a processor, multi-processor unit and a memory which they are communicating with each other, all the machines in that accessing the shared memory, they should all follow the same endianness. But you cannot insist on two machines on the network to follow the same endianness. This may follow big endian or little endian, this fellow may follow something, but what is sent should be independent of whether the machine is little endian or big endian. That is why the network byte order always follows big endianness, so that both the processors who is receiving it, they know what order they are receiving the values. If they are receiving a 32-bit value, they know that in a 32-bit value the higher byte value is coming first in the network, and then the network processor or whoever is reading it, they store it in proper way based on what endianness this processor follows. So they do the conversion of big endianness to little endianness in the especially in this case Intel processors. Okay, when they are receiving it also, they receive it in big endian as, but they store it in the little endian form because they follow that order. Okay, I hope this is clear. Actually, this question what you brought in is actually very apt. Okay, and then means union in C occupies memory as variables are declared in union. Top to down. Yeah, right. Union top to down. Yes. Doesn't matter whatever is the order you are. Okay, let me. Oh, you brought me one more question. It doesn't matter what order you are having. Okay, I will tell you the reason. See, union does not worry about the order in which you are declaring. Okay, I may have a float here, F. I may have a character C. I may have a short S. Okay, maximum size of that. Okay, it doesn't matter whether I am declaring it here union, another union I declare as short S and character C and float F. The compiler goes through all the types and then picks the largest type and then set it, and then how it is stored, that is the size, it reserves for the union type. Okay, and how it is stored depends on the endianness, whether it is suppose if it is starting from the address 100, this is 108, sorry 107, these are the bytes. Okay, how it is storing which value depends on what endianness they follow. Okay, if they are following little endianness, then the lower addresses will have, if suppose you are storing C, it will be available in lower address. Okay, if it is or let me say it is again a compiler, no it's not a, yeah, compiler dependent, but NDNS comes depends on how it is generating the instruction. Okay, I cannot exactly say this because it depends on whether it will sit here or here. If it is a 4-byte value, if it is a only 32-bit value, then I can say for sure it will be here. Okay, but it depends on whether the processor CPU is a 32-bit CPU or 64-bit CPU. But more or less, I can assume it based on the NDNS whether C will sit in the lower address or the higher address based on the type of NDNS being followed. Okay, but it again very specific to the particular compiler. For union to work properly, all variables should be
Hello.
of the same size.
Hello, sir.
Um, yeah, it is
Hello.
a no. Actually, if you are having that kind of a requirement, um, you are right in some way. It will work properly provided you are handling it properly. Okay, I'm not saying that you have to always make sure that all of the same size. Okay, you can actually union has come up not big also for the same size, no doubt about it, but you are allowed to mix the sizes also. But uh, you are allowed to use it. Language does not prevent you, and it will work properly as long as you what you store what you get back. If you are storing a lower value, you have to read the lower value. As long as you are doing it is fine, but you are expecting it to have multiple values at the same time, then there is likely to be some problem. Okay, that you need to be careful. It's very dicey. Okay, I think I am
Hello.
yeah, please go ahead.
Hello. Sir, for example, if in the union we are showing float also, like in the previous problem, USB.c we have set something and US and float also and int also. So in the memory where the union will be stored, which variable will be pointing to what place?
Okay, got it. I got your question. So let me explain a little bit more. I am taking a little more time. Okay, hope it is okay. See, when you have suppose float union you have float f you have, and then character uh, 4. Okay, you have. That means I am like Rohan said, I am taking the same size, 4 bytes, 4 byte. Now it has in memory only 4 bytes. Okay. Now suppose if I write some uf dot f equal to 2.0. Now whatever is the because it is going to occupy 4 bytes for representing this 2.0 in the floating point representation. So it will occupy all the 4 bytes of that value. And then I do u dot character of 3 equal to 0. Okay. Maybe ASCII value or this is not ASCII value. It is a okay, yeah, it's a ASCII of 0. Or suppose assume that I am storing a ASCII of 0, just 0 value. Then now what happens is this is a union U, which is starting at 100, address 100, 100 and 104. Based on the this is 3. Okay, then it will always be here. Always the array value 0 will be here, 1 will be here, 2 will be here, 3 will be here. So this 0 will go and sit here. Now what happens to these values? These values will remain as same 2.0's representation, but this is only a partial value. This is overwritten. Now after that, if you are trying to access f, if you are printing this u dot f, you are likely to get some erroneous value because you have overwritten the part of the representation that you have. So what does the compiler do? It just stores the 2.0 value. After that, when you say this, it will blindly go there, and for the fourth location, it will store the value of 0. So to answer your question, what you write will find the place and then write there. What you read will go to the proper place and read from there. But if you are mixing them, you are doing it at your own risk. Compiler or anybody, nobody can help you. Okay, that's what happens.
Say if instead of character having four values, if there are only two values, then it will occupy only the first two bytes,
Yes, you are right.
and
If car,
the
yeah,
rest will be the same.
yes, rest will not be changed. So if you are suppose you are writing 0, then this will be filled. This will be filled. This will not be changed. Yes, you are right. Okay, any questions, guys? I am saving it. I don't know whether you have immediately class or you are free, whatever maybe.
Hello,
Any?
sir.
Yeah.
So this union itself is so confusing. Why will someone even use it?
Okay. Being in IoT course, you should not ask. I'll tell you. It is so confusing, but it is so important for the IoT guys to know, because you are writing software in a computer or a system where memory is premium. Okay, suppose I am declaring it becomes very trivial when I am having some float value and then some character value. It becomes trivial, but I can have a union and then say, I will say some image. Okay, and then I may have image of, say suppose JPEG or underscore BMP. Okay, and then I have a character or unsigned byte of maybe 2048. Now, okay, this is a very okay. Let me explain you. Okay, what I mean by that. Now, if I have a union of this is unsigned byte. Okay, if you don't understand unsigned byte, and then what I have not shown you here. I will say struct some structure type I have defined. Okay, somewhere I have defined a structure type which is of size 2048. Okay, that size is, I have defined a type def. Okay, and I defined a structure wherein I will say that character, c something called a type, and then I will have some BMP related structure I have defined, and this is similar. This structure is same as BMP. Okay, this actually first byte may be something, second will be something. This is a BMP bit pattern or a image pattern. Suppose I have another structure called JPEG. Okay, I have some structure which is also occupying 2048, and I access it as JPEG image, JPEG structure. Now what I will do inside this union, I will say JPEG structure type, okay, J, and then BMP structure B I will declare. Now what happened, this 2000, even 2048 size is there, or I don't have to have this also. Okay, I want to access it as a byte, I will do it, but as long as I am taking care of these two are same size or maybe little bit offset is there, then I may need this. Suppose one is taking only 1000, 24, another one is taking 2048. I want to mix them both. I want to only reserve only one size. Then I can do this. Now what happens is, what I store is a JPEG image or a BMP image. I can access it based on this type. Okay, I can. It's a ease of writing and accessing the same memory becomes simpler. Okay, and that is how. Oh, now what is the advantage you are getting? You don't need to declare two structures, one for JPEG which is taking 2K or 4K, and then one for BMP which takes another 2K or 4K. I don't need to declare things because I am expecting only one type of image to be processed at the IoT. I have to reserve only one memory. I can store either JPEG or BMP in the same place, and then I may have a type here which will say that it is whether what I am storing is a JPEG image or a BMP image. Then I save memory. I told you IoT has memory constraint. So union will be used in wherever you go. If it is very memory constraint, you may be using IoT, union in the applications like IoT. Okay. Do you understand why union is important for IoT?
Yes, sir, yes, sir. So
So
one more question. I'm sorry, I'm making everyone wait.
yeah,
Uh, So in union, suppose we have a float and the int and the character, and because it is a float, so size of the union will be 4 byte. Let's say the memory is memory. Let's number it as 0, 1, 2, and 3. So when I'm initializing float, it will occupy 0, 1, 2, 3, and then when I'm initializing 2, it will overwrite 0 and 1, and then when I'm initializing the character, it will overwrite 0. Is it so?
Correct. You are right. If I am writing character 0, it will overwrite this. If I am writing character 1, it will overwrite this. Yes,
So
you are
not
right.
character one, just a single character.
Okay.
We have a
Sync.
float.
Okay.
We have a
In.
float, a
Yeah.
character, and an int. When I'm initializing an int, it will write on 0, 1, 2, 3. When I'm initializing the integer, it will overwrite memory 0 and 1. And when I'm initializing the character C, it will overwrite C. Is it so?
Okay.
This is what.
Yeah, your question is clear now. Let me explain. If suppose you are writing only C, assuming that it is a little Indian machine or whatever may be, this is the place where it is reserved for. It is writing it here. Now your question is whether this will be disturbed or not. Whether will it be default made into 0 because I have a I'm writing C. Only C which is having some suppose in byte value FF suppose. That means all ones. This is all ones. Okay, all binary ones. Whether will it be affecting this? Actually, it is supposed to be written like that. Okay, it is actually compiler dependent. Compilers dependent, but compiler now most probably 100% they will try to only change the character value. They will not try to do the other things because they may think that you are intentionally doing it. It will only overwrite here. It will not default write it here. Now your thing is your processor may be a 32-bit processor where the 32-bit processor means the registers are 32-bit. You have register R6 suppose. Your C value FF is here. Other things will be 0. Okay. When it is accessing the R6 and then loading the C value, it will take all the register content and make it 0. It will keep everything like this. Okay. 000 FF. But when it is writing into the memory, and if you are writing only the character C, it will not try to write the zeros into the memory. It will only take out only this one byte and then write it. And based on the big Indian, little Indian business, it may write it here or here, doesn't matter, but it will write only one byte. If a compiler is well written, and most probably it is not expected to be writing more than one byte in this case. Okay.
So whatever the number of variables in the union, it will always start from the zeroth memory and then continue forward, right?
See,
this is what I meant to ask. If it is float, then from 0 to 4. If it is 1, then it will write 0
oh,
to 1.
Okay.
Yeah.
What your question is whether it will start only from here and then write that.
Yeah,
See, again,
yeah.
that it depends on Indianness. If it is a little Indianness, what you are saying is correct. But if it is a big Indian, it will start from here. If it is a big Indian machine, it will start from here. Okay, it because that memory is there, and then it will start from this location. Higher address, it will start.
Yeah, I mean to say from one end, right?
Yeah,
Either
from one end on.
or
Yeah,
from the other side.
correct. You are right. Yeah.
Okay.
Any one of the end, it will start. Yes. Okay.
I'm sorry. Let people leave, sir.
You want to continue anything more? People can leave. I have taken attendance. I'm sorry if you guys are getting bored. I don't know. These are all very important for embedded engineers to know. So Sandeep, do you have any more questions or you are done?
Sir, done for today. Thank you.
Okay, thank you. So where are we stopping? We are stopping at question 8 only, I think. Question 10. Okay. I think 11 and 12 needs more explanation. So let us not rush through. Okay, bye-bye. See you guys. Good night.